Hi guys, Assalamualaikum and good day. This is the next part 3 for shear wall design. In last video, we have determined that our wall is a non-slender wall, and next is the design, okay, for the reinforcement. And we will adopt as the design of column, and in design of non-slender or short column. Okay, this is what we need to calculate. We need to find the MED, the design moment. As usual, before we can design, we need design moment and MED. And the design moment for short column is the maximum in between M02 and also M minimum. Normally it will be M02, but we don't know, maybe it is M minimum, right? So M02 is the one that we have calculated earlier. The higher moment, the highest moment in between okay, the highest moment between top and bottom, that will be your M02, and for this case it will be 18.39 here. Okay, next, this one we have calculate the M02, we have calculate M when we have take into account the M imperfection here, okay, NED times EI, we have calculate this one. We get how much do we get? The M02 is, oh, we didn't calculate it directly, but we just plug in into the formula here. So it should be around 21.8 or 21.9 something here. Okay, we will calculate it later. And next is M minimum here, and for the M minimum, it is also imperfection moment also, which is NED times E minimum. Okay, instead of EI here, where the formula of EI is based on the effective height, now for E minimum, the E minimum is maximum in between H, the thickness of the shear wall, divided by 30 or 20 mm, whichever is greater. And then once we have calculated the M minimum, we will compare with the M02, whichever is the higher value between these will be our MED. And once we get this MED, once we get the design moment, to design a shear wall as we design column, we will use a design chart. Okay, so what is design chart? You have learned this in structural design, in reinforced concrete design in column topic, right? And this is one of the example of design chart. It is based on D2 over H. D2 is just the cover times half of the diameter of bar. Okay. Okay, so just the D2 here. Okay, D2. Some books they use D prime. Okay, and this is your D, right? This is your normal D, or from top to the mid of reinforcement also D. Okay, so and some books they use this D2 over H, okay, or D prime over H. But some books they use D over H. Okay, so the value for the chart will be D. If it is just D over H, it will be 0.8 something, 0.82 or 0.85. But it is the same thing. Just refer to what does the chart wants, whether it is D2 over H or D over H. It will give you the same chart. Okay. All right. Next, once we have determined which chart we are going to use, based on the value here. Next, we need to calculate N over B HFCK. For N is our NED, the 490 something, divided by B HFCK. We calculate that, and also M over BH square FCK. Okay, M here is the MED, the design moment, from previous slide. Okay, so once we have the NED and also M over BHFCK, the NED over BHFCK, and we make a line, and we find out what is the value of this curve here, ASFYK over BHFCK. We want to figure out which curve, okay, if or maybe in between the curve, okay. And once we get the value here, we can calculate the AS we want. AS. Once we have AS, we can provide the main reinforcement. Okay, so moving on to our example here. As I have explained earlier, we will start with the design moment. Okay, so number 3. Number 1 is the action, right? Every action and everything. Number 2 is the slenderness. Now number 3 is the main reinforcement. Okay, and this video is about the main reinforcement only. Okay, for the shear we will cover in the next maybe next 2 videos. Okay, all right. So we know that MED is equals to the maximum between M02 and M minimum. Okay, and this is for non-slender or short. Okay. Alright, so let's figure out M02. M02 is equals to, we know that M top is the higher value plus the M imperfection. We have calculated this, 18.39 plus 3.55, it is 21.94 kilonewton. It is moment, so kilonewton meter per meter. Let me erase it. I did not correctly write that. Okay, kilonewton meter per meter. Next, we want to calculate the M minimum. Okay, so M minimum is equals to NED times E naught, or E naught is the E minimum. Okay, and this E naught is equals to H over 30 or 20 mm, whichever is greater. So the H or the thickness of the wall is 250 divided by 30, we will get 8.33 mm, but this is less than 20 mm, right? So we should choose the bigger in between 8.33 or 20 mm. Okay, therefore E naught is 20 mm. If E naught is 28.33, then we will use 28.33. Okay, whichever is greater, either the calculation of E naught or 20 mm. Alright, so this will brings the M minimum equals to your NED is 490.09, and your E minimum is 20, and this is in unit millimeter. Okay, in our moment in unit kilonewton meter, so divide by 1000 to change to unit meter, and this will give you 9.8 kilonewton meter per meter. So we can see here the MED is the maximum in between 21.94 and also 9.80. So it's equals to 21.94 kilonewton meter per meter. Okay, so once we have figured out what is MED, we want to use the design chart, right? And in order to choose which design chart to be used, we need D2 over H. Okay, now this depends on one more time I said which books that you refer for your design chart. Okay, some books they use D over H, some books they use D2 or D prime. Some use D prime, but D prime and D2 is the same thing. Okay, but normally they will give a figure what does they mean by D2 or D prime. Okay, so for our D2 here or D prime is equals to the cover plus diameter bar over 2. So our cover in previous slide is 30 mm. However, we didn't have the information about the diameter of bar. Okay, so we can assume that we use 12 mm diameter of bar. Okay, so how much? 30 plus 12 over 2 equals to 36 mm. Okay, assume diameter bar equals to 12 mm. Okay, now let's calculate the ratio here, D2 over H. So D2 over H is equals to 36 over 250. We will get 0.144. And for the design chart, let me show you the design chart. We have few design chart. We have few design chart that we can use. So this is the D2 over H of 0.15. Okay, so we have 0.15 and 0.1, right? So in between 0.10 and 0.15, 0.15 is closer to our value of 0.14. Yeah, 0.144. So since 0.15 is closer, then we are going to use 0.15. If you use 0.1, it is also okay. You will get slightly bigger value of ES later on. However, it is thus not wrong if we want to use this 0.15 also. If you want to interpolate, also okay. Okay, in between 0.1 and 0.14, you interpolate 0.15, you interpolate 0.144. It's also okay. Or you just use the closer value, which is in our case is 0.15. Okay, so moving on. So in the design chart, let's write down first. We are going to use design chart. D2 over H equals to 0.15. Okay, and the design chart, we need the NED over BH FCK and also MED over BH square FCK. Okay, at the Y and X axis. So NED over BH FCK. NED is the 490.09 and NED is unit in unit kilonewton. Okay, BH millimeter millimeter, FCK is in unit newton per millimeter square, and therefore our NED should be in unit newton also. Okay, so times 10 power 3. So divided by B, we use B is 1000, H is 250, FCK is 30. So this is equals to 0.065. Next, MED over BH square FCK. Okay, so MED, the one that we have calculated earlier, 21.94, and this is in unit kilonewton meter. Okay, so times 10 power 6 to change to unit newton millimeter. So divided by 1000 times 250 square times 30. So equals to 0.012. Okay. And from the design chart, let's check the design chart. X-axis 0.012, Y-axis 0.064. So 0.01 somewhere here. Sorry. 0.01 somewhere here. Okay. Zero 0.012 somewhere here, not sure where. Okay. And 0.065, 0.0, this is 0. Where is 0.1? This is 0.1, so 0.06 somewhere here. Okay. So it is at the line of a 0 here. Okay. And if it is in this area, it is also 0. Okay. If it is in this area, it is 0. If it is right in the line here, just like what our case here, it is also 0. Okay. So apparently our from design chart, AS FYK over BH FCK is equals to 0. Therefore, AS is also equals to 0. So if you get this AS equals to 0, it means that we need to provide minimum reinforcement. Okay, we cannot have a 0 reinforcement. That's why we have minimum reinforcement, minimum and maximum. That's why we have that limit. We cannot provide less than minimum and more than the maximum. Now for the minimum reinforcement for walls in clause 9.6 here, we have clause 9.6.2 for vertical reinforcement and 9.6.3 for horizontal reinforcement. Now let's look at on the vertical reinforcement. Okay. For your shear wall, you will provide both vertical and horizontal reinforcement. Okay. So for vertical reinforcement, the area of vertical reinforcement should lie in between ASV min and ASV max. So for the value of ASV min for use in a country may be found in its national annex, and the recommended value is 0.02 AC. So this is the AS min for vertical reinforcement. So let's use this one in our calculation. So we will provide minimum reinforcement. Okay, if your value of AS is not 0, then you just calculate the minimum reinforcement, the AS mean, both vertical and horizontal, and you compare it with your AS. Okay, if your AS is more than the minimum reinforcement, then okay. If not, then you will use this main reinforcement as your this minimum reinforcement as your reinforcement. So in clause 9.6.2, okay, so AS mean is equals to 0.002 AC. AC is area of concrete, which is B times H, so 0.02 BH. So 0.002, your B is 1000, your H is 250, okay, thickness of the wall, and this brings 500 mm square per m, okay, and this 500 millimeter square per mm is for the whole area of the shear wall, okay. But for shear wall, you need to provide reinforcement at both area, both surface, okay. You have this surface and you have also this surface, okay. So you will have to provide reinforcement at both sides, okay. So in our case here, this is all 250 mm square per meter for each face, okay. And therefore we will provide, and this minimum reinforcement in clause 9.6.2 is vertical, alright, vertical reinforcement. So provide vertical reinforcement for 250 mm for each face, okay. So in the table of reinforcement, okay, we need to provide 250. Let's check. This one here. Okay, this one is for number of bars, but we are designing per meter square, right? So if per meter square, we are using this table B. Per meter square, per meter. Okay, so we are assuming the 12 bar size. For 250, the lowest in this table is 300 mm. But if we want to find out value that is larger than 300 mm, we can, right? The value of area of reinforcement that is larger than 300 mm for the spacing of bar. The maximum spacing of bar in this table is 300, but we can calculate the area for if we want to provide spacing 350 mm, for example, 375 mm or 400 mm, okay, or 425. But normally we will stick to maximum 400 mm, okay, because we have that normally we have that crack requirement. And normally it will not be more than 400 or 450 mm. Okay, so how do we calculate what is the area if we have spacing, if we want to provide spacing more than 300 mm? So this formula here, okay, you can see this, excuse me. You can see this formula here, 1000 over spacing. So what is the spacing? Let's say you want to provide 350, right? So 350. So 1000 divided by 350 times pi r, for 12 mm, it is 6, right? 6 square. You will get the area here. If it is still more than that, you can try to use 400 mm. Okay. Now let's calculate. Let's try to calculate if we want to provide 350. So 1000 divided by 350 times pi r is 6 square. You will get, if I'm not mistaken, 323. Okay, so the AS required is 250 and we can provide 322, so okay. So provide vertical bar H12 spacing 350 where the AS is 323 millimeter square per meter for each face. Alright. Next, for the horizontal reinforcement. Okay, just now we check for the vertical reinforcement. Next, for the horizontal reinforcement, horizontal reinforcement running parallel to the face of the wall should be provided at each surface. Ni dia dah specifically mention lah dekat each surface. Yang kat sini tak ada. Okay, it should not be less than ASH mean. The value of ASH mean for use in a country may be found in its national annex. The recommended value is either 25% of the vertical reinforcement or 0.01 AC, whichever is greater. So in between this one. Either 25% from the vertical reinforcement that we provide or 0.01 AC. So let's calculate this one. This is for each surface. Okay, for 25% here is for each surface. So let's calculate. For horizontal reinforcement, this is in class 9.6.3. Okay, the AS H mean, horizontal mean, H mean is equals to 0.25 or 25% from the vertical reinforcement, right? From the AS provided vertical. This is equals to 0.25 times 3 to 3. This is equals to 80.75 millimeters square per meter for each face. Or 0.001 AC, right? So 0.001 AC is BH, area of concrete, B times H. So 0.01 times 1000 times 250. This is equals to 250 mm square per meter. So this one is whichever is greater. The greater value is 250. So we will base on 250. And basically, we can also provide the same thing here, 3 to 3 millimeter square per meter. Or let's try if we increase the spacing for 400, okay, times pi r square. This is 283. Okay, and since this is vertical bar, okay, vertical bar is this one here. Okay, you have the vertical bar. This is horizontal bar, sorry. So this is the horizontal bar. Okay, lebih kurang macam tu lah. Okay, alright. Therefore, we will provide horizontal bar H12 400, where the AS is 283 millimeter square per meter for each face, right? Okay, so this is our reinforcement for our shear wall, but we are not done yet. Next video will be, we are going to check for the top story, for the this is the from the level ground to first floor, right? So next we will check for the upper story if we can extend the same number and the same value of reinforcement as this ground floor or first floor. Okay, and lastly will be the shear checking, shear resistance checking, and then that's it. Okay, so we might have another 2 videos coming after this. All right, so this is part 4 for shear wall design. I'll see you in the next video. Bye everyone.